Okay. Okay, so we already talked about, well, you guys know from prior, a neutral solution, right? Where we have equal concentrations of the hydronium ion and the hydroxide ion, right? So water, right? So in the case of water, we know that the pH, sorry, pressing the wrong thing there. There you go. So we know that the concentration of OH and the concentration of H3O plus are going to be equal to each other, right? That's when a solution is considered to be neutral. Right? So we know that's pH 7, right? Because it's based upon the I can't remember the auto of water, autoprotonization of water. Yes, thank you. So, and the case of an acid-base neutralization, we're also going to end up having similar things. The only thing now we're going to have the production of salt and water, right? Okay, so for instance, if we have HCl reacting with NaOH, we're going to end up with H2O plus NaCl. We already know that this is going to be aqueous. This here is aqueous. Q. AQ. Okay. Okay. So water is going to basically one of the products, and then we're going to have a salt. And NaCl is a generic, well, of course, salt, but this is going to work in the case of a strong acid and a weak acid all the time that you're going to end up with this. And even if you don't have a strong acid or a weak acid, you can still end up with this because you guys basically showed that last week when you guys did the polyprotic acids, right? This is great. Okay. So a solution is not necessarily going to be neutral, even though that they may be stoichiometric in terms of the acid and base that's being used. Okay, so, and this is going to kind of lead us to, this is going to be a result of the fact that sometimes when we form a salt, sometimes those salts can act acidically, basically, or neutrally. So there are 4 types of acid and base neutralization. One was the one that I described. When you have a strong acid and a strong base, you're going to get neutral solution form, right? So they're going to balance each other out. The case where we have a strong acid and a weak base, so then that's is going to give us a weakly acidic solution. Okay, when we have a weak base and a strong acid, that's going to give us a basic solution. And then we have a weak acid and a weak base. So it kind of just depends on what ones we have, right? Whether it's going to be acidic or basic. Okay. So I gave you as an example of a strong acid and strong base earlier. All right. That was HCl. Okay. So in that case, we're going to get the formation of sodium chloride as our salt. Oops. Don't ask what I was doing there. Plus water. Okay. Okay. So even though it's a strong acid and strong base, so what effect do you guys expect it to have on your cations and your anions? Yeah. So basically, it's not going to affect it. So we're not going to have, it's not going to change the acidity or the basicity of the solution. It's going to remain neutral. Because it's not going to cause a shift in the formation of the hydroxide ion or the hydronium ion. Okay. What about in the case of a strong acid and a weak base? So let's see. So let me give you an example. See, strong acid, HCl. And a weak base. So what do we expect in this case? No. It's going to end up with a okay. So what is going to be a product in this case? NH4. Okay. So in this case, we're going to basically have an acidic solution, right? That's right. And then we have so we know that this in this case the salt that is going to be formed is just going to be our chloride, and it's not going to be truly a salt. Okay. And so we know that overall we're going to have more cations or anions or comparable. Are there going to be, what is going to be the effect on the cations and the anions? Yeah, that the cation and the anion have in water. So you said it basically is going to be more acidic. So let's see. What about in the case of a weak acid and a weak base? I mean, sorry, a weak acid and a strong base. So let's say we have acetic acid. So H. 2H3O2. And sodium hydroxide. What's going to happen in this case? Did you say nacho? NaCHO. Okay. C2H3O. I've got to remember that. That's good. Nacho. Did you guys think of that? Good. Ah, cool. Okay. So that means, so is this going to be basic, or is this going to be acidic, or is it going to be neutral? Okay. Why is it going to be basic? Okay. So in that case, your hydroxide, because this is a this product here is more apt to stay in this situation than it is to be in this situation, right? Then it's going to lead to more of this being available. Does that make sense? Okay. So this guy is considered a weak acid, right? Weak acids don't dissociate that much. So you're only going to get a small amount of the H plus available to react with this. So that leads to more of this being readily available than the other guy. Okay. Does that make sense? Now, a little bit more. Okay. So if I have a weak acid and a weak base, so can I erase? Let's do hydronium. I mean, not hydronium. Acetic acid. And ammonia. What are we going to end up with? The CHO. No more nacho. Okay. Okay. So this is a weak acid and a weak base. So in the case of a weak acid and a weak base, it just depends on who is more primed, right? So in this case, the ammonia gets a little bit more, right? So the ammonia, more primed. So this guy, which one is going to be more apt to happen? Are we going to be able to get rid of this, the H here, more so than, and if we are able to get rid of the H, more of the H, then we're going to have an acidic situation, right? Because then you have more of the H plus in solution than that negative. Or are we going to have more of that base, right? So if we have more of that base still available, then yeah. So it depends on your arrow. So the arrow itself technically should be like this, where this guy is a bigger arrow going in this direction than it is in that direction, because it's harder for us to separate the hydrogen off of the acetate than it is for the production of the ammonium ion. Okay. So then this would be basic. Yeah. Does that make sense? Okay. So if we have this chemical reaction going on, and what would be the equilibrium constant for this acid? How would I calculate the equilibrium constant for the acid? So products would be, okay. So let's break it down. The products are going to be, before we get to the x squared, concentration of so 6 carbon hexamine plus, or sorry, times concentration of hydronium ion all over concentration So in this case, it would be x squared over 0.233 minus, okay. Okay, so if we had an equilibrium constant for the acid, we could actually sit there and solve this, right? Okay. So let's see. So if I have this reaction, so if we have a, so this would be aluminum pentahydrate ion, and it's reacting with water. And so then we'll get, in this case, the aluminum hexahydrate ion, and then we'd end up with aluminum pentahydrate hydroxide. Okay. So what is the acid and what is the conjugate base in this case? So you're saying this is the acid? So water is acting as our base. Okay. Okay. Okay, so let's assume that the Ka for this is one second. Okay, so okay, and the initial concentration of this is 0.1, 0 molar. So how would I find the concentrations or the pH at equilibrium? Okay, ice table. Okay, so let's do it. Gonna move this over here. Okay, so what is going to be my initial? Okay. So it's going to be ice, ICE. Right here. Okay. Thank you so much. Thank you. Thank you. Sorry, I had lunch all day, so I'm starving. Thank you. Okay. And then okay. So you're saying I don't put nothing? Okay. 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 So then how would I solve? Products or reactants? Okay. So concentration of the aluminum Al, H2O, 5, OH. Times and that's over Al, H2O, 6. Okay, so then that's going to equal 1.0 times 10 to the minus 3 is equal to x squared over 0.10 minus x Okay. So if we assume the 5% rule, we are going to ignore this. So then we're just going to go x squared over 0.10. So then we get 1.0 times 10 to the minus 4 equals x squared. So then x is going to equal, what was that? Doing what? Okay. So we take the square root of both sides. It's going to be 1.0 times 10 to the minus 2. Okay, good. Yeah, no, maybe. You got me chicken? Perfect. I do like chicken. I like everything, so yes, crispy is good. Yes. Oh, that's fine. Yes, I need the caffeine, so that's perfect. Thank you. Okay. So what would be the pH? Okay. Okay, so pH equals minus log the concentration, right, of H3O plus. Okay, I'm running out of room again. So then pH equals 2. Okay, questions? Concerns? Cash or Kool-Aid? It's all coming back? Okay, clear. Okay, so we've already kind of talked about polyoprotic acids. So, or I should say, monoprotic basically means that we're able to lose that one H. Polyprotic means that you have more than one hydrogen to lose. So for instance, we had talked earlier about HCl, right? So that would be monoprotic or polyprotic. Okay. Now what about H3PO4? Okay. So in reality, what happens is that when an acid is polyprotic, it's going to ionize in steps. So if we have H3PO4, AQ, it's going to PO4, we have 2. Okay, then this guy, H2, PO4 minus and then that last step. Okay. So the equilibrium constant is going to get smaller as each step starts. So the equilibrium constant here, this first one, is going to be greater than the second one, which is going to be greater than, the third one. Gotcha. Yeah. So what does that mean? Oh, you're talking about. Why does it make you cold? I'm 21. No, I'm serious. I'll show you my. I heard 22. Yeah, you better. What's going on? Yeah. What's that? So what does that mean? The question. There's nothing? What was that? They're comparable to each other? No. It's decreasing as we go down. What did you say, Julia? Yes, I'm talking about the equilibrium constant. Yeah. So let's look at it simply. Which reaction is going to have the highest pH? What was that? Why? Because its equilibrium constant is going to be larger than the others, right? It's going to be favoring more of the products, right? It's going to have more favor towards those products. So you're going to have more of your hydronium ion in this case than you would have here. Does that make sense? It also should be a dead giveaway that the very first reaction is a Ford reaction. It's not an equilibrium reaction. You guys notice that? Good. Sorry, starving. The hydronium. Yeah. Because you notice that the arrow here, it's not equilibrium, not going both ways. Okay. So types, we have diprotic. Diprotic basically means what? 2. That's right. So we're able to lose 2 protons. And triprotic, we're able to lose 3 protons. So H or phosphoric acid is going to be what type of? What was that? Did you say triprotic? What did you say? So it's triprotic, right? Because it's able to lose 3 protons. So give me an acid that would be an example of a diprotic. H, did you say H what? H2O? Not quite. OH? You're just putting things with H in it now. OH is the hydroxide, right? So, but that would be the product of this guy, right? That would be H3O plus OH, right? You can't lose another hydrogen in this case to get the oxide. So no, that wouldn't quite work. So H2PO4 minus, is that what you're saying? Well, that's not quite, I mean, it would be, but not quite what I'm looking for, not the ion. We're going down the list. Come on. Anything else? Hydrocarbonic. H2 carbonic acid, right? Not hydrocarbonic, carbonic acid. Yes. So yes, this would be an example, right? Because we can lose the first one, and then we'll get HCO3 minus AQ. Right? So that would be, and then it was able to lose the second one. Okay. No, it's not hydro. Hydro means that it doesn't have oxygen. All right, like this here is hydrochloric acid. So you would say hydrocarbonic acid. This is what you would assume hydrocarbonic acid to be, H4. Struggling here. Can't do it with my right hand. H4C, right? Sorry. Which is methane. And methane, when you boil it and put it in water, it doesn't make an acid. That's one of those that doesn't. So H4C, right, which is CH4, methane, right? So that does not exist. Carbonate does, right? So carbonic acid does exist temporarily, but then it breaks down to carbon dioxide. Yeah. Okay. Product. So I'm not quite understanding what you're asking. So let's try to reframe the question. So you're saying, are you saying that the loss of the proton occurs naturally? So the first one, right, the loss of the very first one is going to be, well, technically they all occur, right? So if you have them around, they're going to happen, right? So for instance, in the case of the phosphoric acid, this here is going to happen very fast. As soon as it hits solution, that's already happening. It's instantaneous. This one, it happens, right? But it's going to be dependent on the concentrations of this guy and that guy, right? So in our solution, if we have a lot of this, right, it could drive the reaction in this direction. If we have a lot of this, it could drive the reaction back the other way. But we know that we have a lot of this, right? Because this is happening. So in this case, we're having a lot of these. So they're all being driven back here. So you're going to have more of this present, and you're also going to have some of this present as well. Okay. Does that make sense? Because we're getting a lot of this. And that's going to affect this. Okay. So, interesting question. Okay. Okay, so let's assume that we have, since you're talking about carbonic acid, so let's assume that we have 0.3 molar of carbonic acid. Let me erase this so you guys can see something. Okay. Okay, and let's assume that we have Ka equals to 10 to the minus 6. Okay. And then we have Ka equals 10 to the minus 13. Okay, so those are your two equilibrium constants. So knowing that, if we're starting off with this amount of carbonic acid, what is going to be the pH of the solution at equilibrium? Okay, first thing I'm going to need to do, let me write my equation. All right. Okay, so if I have H2 CO3 AQ plus H2O so is carbonic acid a strong acid or a weak acid? It's a weak acid. How did you know? Carbon. Excellent. Okay, so we know that it's going to be equilibrium here. So what are going to be the products? Hydronium ion. Okay. Okay. So we're going to use one of the H's. So then we get bicarbonate. Or hydrogen carbonate, right? Okay. So you're saying I need to write another equation? Yeah. Okay. Okay. You mean carbonate? Yeah. 2 minus, right? Okay. So what's next? Ice table. Okay. For the first one? Okay. Okay. Initial concentration. I feel like I'm missing something. Fine. Okay. Nothing. Okay, so just put a bar here. 0, 0. Okay. Okay. So then we get Ka1 is going to equal concentration of H3O plus. That's right. That is correct. Okay. So then we plug it in. What assumption can we make? Okay. So then that's 0.0033. So then we get, let's see, 3.3 times 10 to the minus 2, 3, minus 9. Equal to x squared. So x is equal to can anybody do the math for me? What did you guys get? 5. So now I have a question for you, right? So this would be the this would be the concentration of H, of the hydronium ion and the sodium bicarbonate ion. The bicarbonate ion. Okay. True or false? It's true for the first one. Okay. So could I use this for the pH? Would the second reaction make a significant contribution to the concentration of the hydronium ion? Okay. Because I brought this over and multiplied it by my Ka, which is times 10 to the negative 6, right? And does that give me 3.3 times 10 to the minus 9? So that's 1, 2, 3. Are you sure? Oh, did I put too many zeros? 1, 2. Yes, you're right. Negative 8. I got carried away. You're right. I wrote 3.3. I wrote the wrong number down here. So yes. Well, it should, well, not significantly, but it should change it. It should change it by a factor of, good question. My bad. So it's 5.74. Okay, so give me the new number. Okay. 8, 2 times 10 to the negative 4. I don't think it's your calculator, because if you take the square root, because we're taking the square root of both sides, right? So yeah, okay. Okay, so good question, good correction. So then my concentration, my starting concentration for the next one would be this, right? It's at equilibrium, so then we'd assume, so that's going to be the starting concentration. This guy would start off technically at 0, right? This guy's going to start off at 0, right? So, and then I'm going to put X1, X1. So my question, so then this guy would be minus X1. Okay, so my question is this value going to make a significant enough of a difference to change our pH? Well, let's do the math, right? Easiest way to figure out is to do the math. Okay, so if we have Ka, Ka2 is going to equal 10 to the minus 13. And that's going to be equal to X1 squared all over 1.25 1.82 times 10 to the minus 4. Okay, I'm going to move this up. Can I get? I hate this. I hate when I don't have enough room to move this up. Move this up. Okay, so what can I assume? 5%. I forgot minus x1. Okay. So if I assume 5% rule, I'm neglecting this, so I just get x squared 1.82 times 10 minus 4. So then I get 1.82 times 10 to the minus 17 equals x squared. So x1 equals what? Equals 2. I'm asking you. 4.26 is that times 10 to the minus 9. Okay. So is the contribution of that second reaction going to be significant enough for, yes, those are good to use. Are those going to be significant enough to add to the concentration of the hydronium ion? You're going to say no? Yeah, it's too small. So it's just going to be that first reaction. And that's what you guys are going to see. Not in all cases, but in a lot of cases is that first reaction, reaction is where your pH is going to be pretty much dictated, right? Because that second reaction, depending on the Ka, of course, is going to be minimal, right? There is a chance. It's rare, but there is a chance, yeah. But I mean, if you see like a jump like this, where we go 10 to the minus 6 to 10 to the minus 13, right? No, right? Yeah, you can determine it by looking at the first one, but you'd want to say, if you got a question like this, you'd want to say that, hey, since the pKa is so small, the amount of hydronium ion will be minimal produced at equilibrium. Because it also suggests, what does that suggest since that the pKa being small? Would that suggest that you're favoring your products or that you're favoring your reactant? What was that? Your reactant, because the value of your pKa is so small, right? Say it again. It's the log. So anytime you put a P in front of, like P in front of H, right? pH, right? That's just a log, the minus log of that concentration. So it just allows us to put it in a nice linear scale compared to an exponential scale. Yeah, if your pKa, if your pK, that isn't true. So if your pKa concentration, if your Ka is lower than, because your pKa is always going to be the log, right? It's going to be the minus log. So what I'm saying is that if the second Ka has a pK that's greater than your first Ka, yeah, okay, yeah, it's my fault. Yes, let me clarify. I should just say your Ka, right? So since this Ka is so small, then it's going to have minimal contribution to that hydronium. Does that make sense? Okay. Okay. So buffers. So let's see. So you guys have already been doing this in your homework assignments. So buffer solution is just basically a solution that contains an appreciable amount of both a weak acid and its conjugate base, or a weak base and its conjugate acid. So buffer solutions basically are going to be resistant to changes in pH upon the additions of strong acids or bases. So in other words, you're not going to see too much of a change. It takes a while for it to sit there and shoot out. So here's an example. This guy is unbuffered. This is a buffered of 8. Okay, a pH of 8 buffer. So, and this is the case of, this is where we're starting off at. Okay, and so we're using methyl orange, which is a nice yellow color, right? And then after we add 1 ml of 0.01 molar of hydrochloric acid, so we spiked it with acid, we see that the methyl orange turns orange, right? Which means that the solution now is a pH of 4, right, roughly. So in the buffer solution, you saw that didn't see a change. So how does buffer works? So a buffer is going to basically work. They're going to have to be good enough to get rid of the strong acid and strong bases. So adding the hydroxide ion or adding the hydronium ion, they're going to basically be consumed, and therefore they're not going to have an effect on the pH. So your buffer solution should be interacting with those guys to keep them from affecting the solution. So any add of hydroxide is going to convert into basically a weak base, and any add of the hydronium ion is going to be converted to a weak acid. Okay, so in other words, it's just going to keep everything neutral because it's going to basically interact with that. Okay, so basically you're kind of spiking the solution with a combination of a weak acid and a weak base that won't allow them to be shifted in any direction. So often we use acetate, right? So this is an acetate buffer. It has acetic acid and then sodium acetate. So a change in the amounts of your acetate and your sodium acetate are going to basically result in a very small change in your pH. Yeah, that's right. So in other words, you're kind of spiking the solution with both. So we have acetic acid and you have acetate that are added in there. And so the acetate, it kind of keeps it at this very, not neutral, but it keeps it leveled off. So even if you add some acid, it's not going to change that pH, right? It's going to keep it around 8, right? And then if you add a base, it's going to keep it around 8 because you're spiking it with both the base, yeah, That's right. And so this is just basically showing you that. So if I add hydronium ion, so I add acid, it's just going to shift it here. So then I end up with more of my acetic acid produced. And then if I go the other way, I end up with more of my my base being produced. So right now it's even. I shift one way, more base. If I shift the other way, more acid. Okay. So let's assume that we have a 0.1 molar buffered solution. Okay, so it's buffered with acetic acid and acetate. Both at 0.1 molar. Okay. Okay. So calculate calculate the pH let's do actually let's do HCl. Oops. Okay, wait, hold on. Assuming P. Sorry. Where's my okay. Okay. So I haven't taught you guys that, but yes, you can use that to get to this answer. But not using that, see if you guys can figure out the other way, because the Heisenberg equation is basically solving for this for us. not much faster. Hawkenbot, not Heisenberg, but Hawkenbot. Too bad. Actually, let me fix this. This should be 5. And that should be 8. There you go. You said the first rule is to set up. Okay. So what is our chemical equation? Okay, acetic acid. So H2 H3O2 Is it going to be plus acetate? Mm-hmm. Because what is the product of adding acetic acid to water? I get H2O plus H2O, and that's going to yield what? It's going to yield the hydronium ion and what? And acetate. Does that make sense? That's right. Okay. So if that's the case, what am I going to do next? Okay. So what does the hydrochloric acid do? What is it really doing? It's going to ionize instantaneously, right? So what is it really doing? What is it adding to our solution? It's adding hydronium ion. How much hydronium ion am I adding? So what do I need to do? What was that? Ice table. Okay. So if I have my ice table, what is my initial? 0.1 molar. Okay. And then over here, 0.001. Okay. And is there anything else? I'm going to put 0 here. Are you sure? Because I have a 1.10 molar or buffer solution of acetic acid and acetate. What does that mean? I had them both. Yeah. So I should have a start off value of 0.1 molar. Okay. So my change minus X okay. So my equilibrium and okay. And this is? Okay, so my K A is going to equal X plus 0.001 times 0.1 plus X all over 0.1 minus X So if I assume the 5% rule for all three of them, then I'd have nothing to work with, right? Yeah. So if you just assume 5%, you ignore this one, we'll ignore this one, and we'll ignore that one. So just assume the 5% for the bottom. So we could do that, yes. But then that still gives us a quadratic equation up here, right? We just have to work it out. But don't worry about working it out. I just wanted you guys to get to this point. Don't work it out. Yeah. Okay. Okay. How are you guys feeling? Are you getting it? You see how this works? Because the buffer solution is going to be in equilibrium in itself. That's what we're looking at initially, right? And then all we're doing is we're shifting that equilibrium by spiking it with just H plus. Yeah. That's right. Yeah. Okay. Okay, good. Let's move on. Clear? Okay. Next. Okay. So often when we talk about buffers are going to have a buffering capacity. So in other words, it's basically going to give you that volume that you can add before you start changing the pH, significantly changing the pH. Now, every buffer has a buffering capacity. So you want to kind of pay attention to that when you're using buffers. Okay. So, okay, I'll go back. Yeah. So what I mean by buffering capacity is that, so for instance, if we keep adding acid, eventually we'll get to the point, exactly. We'll get to the point where it will start affecting that pH, right? So then that means that the pH is going to drop to lower than what it is. So eventually all of the H pluses are going to react with the conjugate or with that base, right? And so then it's going to be sucked up. So then once they're all gone, then you're not going to have anything that's going to bind it that's keeping it from affecting the pH. Does that make sense? Okay, so eventually you're going to reach that limit. There's always going to be a limit. So, and some buffers are better than others, like for instance, the phosphate buffer. Well, why do you think the phosphate buffer is so good? It has a pretty wide range because phosphate, what is phosphate? What's the chemical formula for phosphate? PO4, right? What's the charge? -3, right? So that means it can add how many H pluses? 3. So pretty sexy, you know, because you can add so many H's on there, it gives it a lot more of a range, you know. Okay. Okay, so when we talk about that buffering capacity, that's going to depend on the number of moles of that weak acid and its conjugate base, right? So depending on how much you actually have to actually buffer it. So the more moles you have, the higher the buffering capacity. So if I have a lot of phosphate, right, in there, then that gives me a large range, right? So if I have, because usually what they use for buffering, they'll use one of the ions or both of the ions, the ionic form. So the dihydrogen phosphate, and they'll use the hydrogen phosphate that will act as their acid, and then the base is going to be just the phosphate ion. Okay. Okay, so once the buffer is depleted, you're going to get a huge spike in your pH, right? Or a huge change in your pH. I shouldn't say spike. It could be a spike or drop, depending on which way you're going. Okay, so this is just basically showing you that. Okay, so again, they're using methylene orange, and so it's buffered at a pH of 8. So to the left, so now it's at 7.66. And so after we've added a whole bunch of acid, and this is just when it's shot over, right? It drops immediately to 1.55. And that's just like the addition of a single drop puts it over the limit. Okay. Okay. So the Henderson-Hawkenbot equation, that's what we're getting to. So this is just the general equation for an acid, right? So here, this is representing the acid, the weak acid. This here is going to be its conjugate base. Okay, so using the Henderson-Hawkenbot equation, this here, we can calculate the pH is going to be equal to the pKa, which we now as the log of, plus the log of the concentration of the conjugate base over the acid. Okay. It's minus log of the Ka. So. Okay. Okay, so if we calculate the, okay, so if can we calculate the pH of this buffered solution? So we know that the pKa, or I should say the Ka, this is acetic acid again. So the Ka of acetic acid was 1.8 times 10 to the minus 5. Okay. Are you saying something, Abel?
No.
Okay. Who are you? Ah, good. Okay, do you have a value? So what am I going to use in this case? Which equation am I going to use? Henderson Hawkenbot. What was that? The new one. Oops. Okay. So okay. 8 times 10 to the minus 5 plus log 1/1, which would be, okay, so log of 1/1 . Okay. So because we know log of 1 is what? 0, right? So it's whatever this value is, right? Okay. So if we're comparing buffer 1 to buffer 2, we know that the pH of them are going to be the same, which is going to be 4.74, right? But which one is going to be more effective as a buffering agent? Buffer 1 or buffer 2? Why? Okay. Why? It has a highest molarity, yes, because it has more things to bind stuff, right? So if you have more acid, it has a lot to bind the acid, and it also has a lot more to bind the base as well too. Okay, where the one below it is a tenfold concentration lower, right? So it's gonna bind less. Right? So we're probably gonna run out of this guy before we run out of that. In other words, does that make sense?
Yeah.
Okay. Let's see. Let's wrap up. And what we'll do is do questions. Have you guys finished this yet? Finished. Although we're almost done. We have 8 more sets. Do you mind if we do a little more lecture? Just a little bit more? So we can finish these slides and then we can get to the next set. Okay, clear. So I'm excited to get to the next set. Next one is going to be pretty short. It's still equilibrium, but it's a little different. Okay, so this basically is just showing you a buffered solution. All right, so you guys can see as we add more and more and more and more and more and more sodium hydroxide, we got very little change occurring, right? And then all of a sudden we sheet up, right? So this is an example of how a buffer solution is going to work. Yeah. And you guys kind of saw that when you guys were your curves. Yeah. So, and you guys will see that when you guys do it, Abel and Marcel. Okay. So acid and base titrations. Well, you guys are already familiar with this. You guys should be pros at this because you've done it so many times, right? Yes. So, in the case of acid and base titration, so they're basically always going to be, there's 2 types of titrations. So one of the types of titrations is when you have a strong acid and a strong base, and you're titrating them out, or you have a weak acid and a strong base. Okay. So those are the two typical types of titrations. Now, technically, you could go the other way around, where you have a strong acid and a weak base as well. Okay. Now, the equivalency point. What is the equivalency point? Yeah. Okay. So if we're strong acid and strong base, we basically get neutralization, right? So our equivalency point will be 7. But when we have a strong acid, a strong weak acid, and a strong base, is our equivalency point going to be 7? That's right. We get that plateau effect happening. That's true. That's sort of what you guys saw. Well, or you get, in the case of yours, you had 2 spots, right? Because you have a polyoprotic acid that we're using. Okay. Okay. So in the strong acid, strong base, the pH is going to start off low. And then as we add more and more base, we're going to get a gradual increase in the pH, right? So strong acid, strong base, hydrochloric acid plus sodium hydroxide yields water. So the midpoint in the curve is going to be our equivalency point. In this case, our equivalency point is going to be 7. So as soon as we start exceeding that equivalency point, then it's going to become basic, right? So we're going to have pH that is going to be greater than the equivalency point. Okay, in the case of a weak acid, strong base. So an example of this is acetic acid and sodium hydroxide. So again, we're going to get water and then we're going to get acetate. Okay, so now this titration curve is going to be somewhat more complicated. So it's going to be very similar. The difference is that, again, we're going to start off with a low pH. No, it should still it should gradually increase, but then there's going to be a point where your equivalency point is not going to be equal. Yeah, and you're going to get a plateau effect happening for a bit. So until you get to a certain point, right? So then initially, you're going to get the gradual rise of your pH. And then your midpoint is going to be the part of the curve that is vertical. So it's going to go this nice straight up. So your midpoint for a while is just going to shoot straight up. Okay. And I'll show you what that looks like there. And so in this case, the equivalency point is going to be 8.72. Okay. So if we look at this, so this is a strong acid, strong base. So you can see the equivalency point. So this is my equivalency point, which is going to be at a pH of 7. And then here, this is a strong acid and a weak acid and a strong base. So my equivalency point is 8.72. Okay. So what does that mean? So if we have a weak acid and a strong base, our equivalency point is going to be at a pH that is acidic or basic. Basic. If we have a weak base and a strong acid, then our equivalency point is going to be acidic. Yes. So just what we talked about earlier, right? So when we get to equivalency, right, it's going to shift, right? Because it's a weak acid, because you still have things that are not separating the way they're supposed to. Does that make sense? And it makes sense if you think about it, like acetic acid is a weak base, right? So it's going to try to keep that hydrogen. We're going to have more of the things that are associated with the hydrogen still attached, right? And so it's going to take more of that base to get that dissociation to happen. Okay. Okay. So acid and base indicators. So an indicator is basically what we use to identify a titration has happened, that we've reached an equivalency point, or that we reached a certain pH. Okay. So often acid and base indicators are going to be different colors, right? So depending on the range of our acid, they're often derived from plants. So there'll be dyes that we get from plants. There are dyes that we use in clothing, like indigo and things like that. A lot of those dyes are actually acid and base indicators. So if you guys bleach some of your clothes, right? Bleach, is that going to be acidic or basic? Bleach is basic, right? So the fact that it bleaches some of your clothes, like it fades them and makes them, that's because some of the chemicals that are used in your clothing, dyes, are just indicators. Only thing, and don't recover, right? One and done. Okay. Yeah, same with hair. Yes. Okay. So you guys can see here. So these are various indicators that are currently on the market. This here is this is basically an indicator that we use in the lab. It's called the universal indicator, which has a combination of all of the different dyes all together. Right. So like here we have crystal violet, we have what is that? Chrysol red, thymol blue, erythrocin B, yeah. Yeah. 2.4 dinitrophenol, bromophenol blue, methyl orange, which you guys have been familiar with so far. Bromochrosol green, methyl red, etherochrome black, bromochrosol purple, alizarin, bromothiol blue, phenol red, N-nitrophenol, O crosol phthalinin, and phenolphthalein, and then thymophthalate and aerosol yellow, right? So not alizarin yellow R, okay? So, and this kind of gives you the range of the colors that they are, and it is a very wide range. Or you could use cabbage juice or cabbage extract, right? And so that's also, which we found out last week, can't use too much of it, right? Or not last week, was it? Yeah, it was last week, huh? 2 weeks ago. Gosh. Okay. And so you can use the different indicators to try to determine equivalency points if you have a weak or strong acids. So depending on the indicator, depending on the pH that you're looking at, you're going to pick your indicator. Okay? Questions? Concerns? Cash? Okay? Take a break. 10-minute break, and then we're doing problems. Can you guys see it at home? Abel and Marisol?
Yeah, I can see it.
Okay.
Yep.
Okay. Okay, so it says, let's see, construct the expression for Kb for the weak base NO2 minus, so nitrite. So we have nitrite solution plus water yields hydroxide ion plus nitrous acid. Okay. That's right. Well, you don't include water, period, because it is a liquid. So if it's a solid liquid, we're not including it. The only thing that we would include are gases and aqueous solutions. So what's on top? OH. H292. Okay. Is that all? Okay. NO2. Okay. Any other question? What about you? You guys in Fireball, do you guys have any questions?
Not yet.
Okay. $53. Okay. So it says determine the concentration of C6H5N H3 plus in a buffered solution. To determine this, construct an ice table, part 1, Then write the expression, the equilibrium constant expression, part 2, and use the information to determine the concentration of C6H5 and H3 plus part 3. So complete parts 1, 2, 1 through 3 before submitting. Okay. 1. So ice table. It says the buffer solution contains dissolved C6H5N2H2 and C6H5NH3Cl. The initial concentration of C6H5NH2 is 0.5 molar. The pH of the buffer is 4.2. Let X represents the original concentration of C6H5N3 in water. Okay, so where am I starting now? So I'm gonna put a dash there. Okay. Okay. Then next. Okay. What was that? Zeros for everything else. Are you sure? Okay, read the question one more time, and then I'll write down whatever you tell me that I need to write down. Is this the one that we did? What does it say? It says let X represent what? So the original concentration of, so which is the same thing as this, right? Because the chlorine is just it brings it to the party, right? So then we want X to represent that. Okay. And so what is going to be our change? You look like you're bored. Did you finish them all? You did. Okay. The next one. What is pH? What does pH represent? Okay, so it's negative log of, so it's, what would be 10 to the negative, because isn't pH equal? If we're given the pH, this gives us our concentration, right? So pH, well, first off, do we have any hydronium ions? Because this equals the negative log of the hydronium ion, right? In our equation, are we looking at a hydronium ion? We have the hydroxide. So how can I calculate the concentration of the hydroxide ion? PO. So what do I know? I know that pH plus PO equal what? So then PO, I'm sorry, POH, sorry, is going to equal 14 minus pH. So then that's 14 minus 4.2. So I get 9.8 is my POH. So then how would I figure out the concentration of the hydroxide ion? How do I figure out the concentration of my hydroxide ion? All right. I just take the log. I take 10 to the power. Sorry, got ahead of myself. So to change this back into concentration, I would go, because we know that this is minus log. Minus log the concentration of OH. That's going to equal, in this case, 9.8. So if I bring the negative over here, so then I get minus 9.8 is equal to log concentration. I know that this is base 10. So then if I take this to the 10th power, take this to the 10th power, then I get concentration, OH, equals 10 to the minus 9.8. Okay. Does that make sense? Do you want me to move this so you can actually see it? Yeah. Okay, so if you guys can give me the value, if I don't have my phone or a calculator. Oh, so 1.6 times 10 to the negative, okay. So that's going to be this value, right? So that's going to be how much OH that we have at the end. And that's also going to be our change, right? So then what do I need to put here? subtract it. Okay, so I'll take and so then I get so then what is this going to be over here? The change. So then I need to put this as change, right? Okay, so if I do this, this value is going to be essentially I have to put dashes here. Okay, so that's the first part. Okay, so my equation. So my bottom is going to be what's going to be on the bottom? Is it 0.15? I'm sorry, 0.5. Okay, what's going to be on top? Okay, so you're saying this times x plus this, right? Or did I screw up? Okay, so then I need to solve for x. So let's do nine. Divided by 1.6 times 10. And that's going to equal x plus 1.6 times 10 to the minus 10. So that I get x is going to equal 9 divided by 1.6 minus 1.6 times 10 to the minus 10. What did you guys get? Is that 1.2? Okay. Show the answer. Bam. Awesome. You got it correct. Okay. You guys see that? It's a lot of steps. Okay. Next problem. 61, you said? 61. Yes. No, they're not simultaneously. So concentration is just concentration, right? But typically they're talking about concentration at equilibrium. Yeah. Yeah. So when they're talking about concentration at equilibrium, it would be this. In this case, they just wanted to know what was the initial concentration. In that case, we were just solving for the x. That was yeah. Okay, you said 90, 61, right? Yeah, let me guess, there's only 50, 60 problems, right? That's right. I can add some more, you know. Oh, 61 is the last one. Okay, so I have to click on, oh, I'm on 3. Oh, is this the one that I restarted? Give me a second. Yeah. There you go. My computer's been doing that like crazy. I've been trying to work on a program review for the last month almost, and it crashes critical moments before I get a chance to save it. Okay, it says a student was titrating a solution of HC4H7O2 with a strontium hydroxide solution. Determine the pH at a particular point in the titration. To do this, construct a PCA table to determine the moles produced. The mole product formed after the acid-base reaction, part 1. Construct an ice table to determine the concentration of the hydroxide solution, part 2. And then the equilibrium constant expression, part 3. Use this information to determine the pH, part 4. Complete 1 through 4. Submit your answer. Okay, so it says 40.0 mils of a 0.22 molar H4H7O2 solution was titrated with 10 mils of 0.1 molar strontium hydroxide, which is a strong base. Fill in the BCA table with the appropriate values for each involved species to determine the mole of reactant and products after the reaction of the acid and base. You can ignore the amount of water in the reaction. Okay. What are going to be your moles before? What was that? I have to convert stuff. So I have molarity. How do I change molarity into moles? Do I need the molar mass? Molarity to moles. It's moles over liters, right? So I have milliliters. So I need to looks familiar. Did we do this one too? And you guys have to do the calculations. Okay, thank you. So I can ignore my water, is what they tell me. So I can do that, is that what they said? You guys know what they said? Didn't they say I could ignore my water? Ouch. Right here. Okay. And then for the hydroxide. Okay. And so initially I have how much of this? Say 0. Okay. So then my change is going to be who did? Good. How did he do that? That's horrible. Okay, so what do we need to do? What's going to happen? So what is going to be the change? So we have our chemical equation here, right? Is that true? Yeah, chemical equation's right here. So what is the chemical equation? Okay, so we're going to subtract what's being used, right? So what's going to be used? Are they going to be used comparably, or are they going to be used not comparably? The other thing that we want to do is want to pay attention to, there's one other thing that we need to pay attention to. What was that? The arrow. Okay, so this is what we're using, right? Is that true? We're using this guy. So if we're using this guy, how much hydroxide do we actually have? You remember what we did here? So for instance, this is 0.1 molar, right? And that's for every 1 mole of SrOH2, how many OH2s do I have? What was that? So for every 1 mole of SrOH2, how many OH2s do I have? I mean OH, not OH2. How much OH minus do I have? I'll have 2, right? Okay. So if this is the number of moles of Sr, that's right. Yes, the initial concentration of OH is wrong. Yes, because we didn't take into consideration. Yep. Okay. Right? Okay. So this brings us to our next point. So now this reaction here is a 1-to-1 reaction, right? You guys agree to that? Okay. So if this guy is a 1-to-1 reaction, which one is going to be limiting and which one is going to be in excess? You guys remember that? So who's limiting? Hydroxide or the HC4H7O? The hydroxide would be limiting. Okay, so then we're going to be able to use up all of that, right? So then shouldn't that be minus this, right? So, and then what's going to happen to this guy? Minus the same amount, right? And then over here, this is going to be it's a 1-to-1-to-1-to-1 ratio, right? Okay. So then what's left here? And this guy is okay. So now we're able to get to our next table. Okay. So what is going to be our initial? Okay, before we go there, let's pay attention to something. What does this arrow mean? And how is that different from the arrows that go both directions? You can go to that conversation too. Yeah. That's right. We can't go back to the reactants, right? So that means that whatever we get here is going to be kind of like our starting off point for this next one, right? Okay. So what is going to be our starting off point for the next reaction? Now remember, this is molarity. So I have to divide it by what? Divide all of our values by 40 plus 10, 50. So if we divide everything by 50 mils, and we got to change that mils to milliliters, I mean liters, that is our total volume. That's right. So you guys have to do the math. So it would be 6.00 times 10 to the minus 3 divided by 0.05. 0.05. Yep. So that would be what? It's 1.12, 0.12. Okay. Then this would be the water. Okay. And then our initial OH, I'm sorry, OH, H3O plus is going to be, let's go back to the 0, okay? And then our initial, are you sure? Let's take a look. Don't we have something here? We're primed. Is it 0.4? I don't know. Is it divided by 50? What is our point 0.014? 0.4. 0.4. Okay, right here. Okay, so our change so this one is negative X. Okay, and we have nothing going on with the water. And so then this is going to be X plus X. Okay, and then this one is going to be also plus X. Okay, and then at equilibrium, oops, sorry, positive X. Okay. So our equation is going to be okay. Oh, sorry. 0.04. Okay. So we need to solve for X. Figure that out. I'm just going to sit up here and look pretty. Remember the fact that we did the function? Yeah. Because it was subtracting that value. It worked for this one. The other one it didn't work for because where X was located at.
And how come OChem uses Pearson instead of Chem1B?
Another use Chem1B.
Could I see you on your slide?
Because I gave Pearson their slides. So all their images and stuff come from there, from their book. What you guys get? For your pH? Okay. Questions? Concerns? Do you guys have any other questions that you want to look at? That's it? Yeah. Yeah, a lot of algebraic manipulation, right? And you got to remember the rules. Well, log, what is log equal, you know, and yeah. Me, my problem is that I always mess up writing the numbers. So I'll screw up because, oh, as you guys saw earlier, right? Like 0.000. Uh-huh. Another, and then with these problems, it all has to be right. Although Solomon figured out a way of narrowing it down. He does one step and he just puts blah, 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 and then it'll take you to the one that's wrong first. And I'm like, huh, that's good. Beating the system, I get it.
I don't want to do all that. If I were not affected,
Yeah. Yeah. Okay. Questions? No questions? Any concerns? Okay. What about you guys on the other side? Any questions?
I'm all good.
You know, here's one last opportunity for me to do one more problem.